Welcome back, AP Chemistry students, to Unit 9. Today we will be talking about Unit 9.5, when a voltaic cell is at non-standard conditions. Galvanic cells are a chemical reaction where one thing is oxidized and another is reduced. And like all chemical reactions, it's not given that it will definitely occur. A voltaic cell will only function if it is thermodynamically favorable. Now we can calculate if it's thermodynamically favorable by determining its Gibbs free energy. Remember, a negative Gibbs energy will be a reaction that occurs. We can calculate the Gibbs energy of a galvanic cell by using the formula delta G equals enough, or delta G equals the moles of electrons transferred times Faraday's constant times the cell potential. If we are looking for a negative Gibbs energy, as long as this expression is positive, we'll end up with a thermodynamically favorable reaction. Or simply, as long as the cell potential is positive, we end up with a battery that functions. This is why I've been having you note how many electrons are transferred for your voltaic cells, because we will need that information to complete this, because we're going to take the moles of electrons and the voltage and multiply by Faraday's constant, which is the amount of energy 1 mole of electrons can give off for each voltage. So by multiplying by moles and voltage, we get a unit of energy for joules. Now, a Faraday, you could remember, is 96,500, but it's also on your formula sheet right here, that a Faraday is 96,500 coulombs for each mole. In exercise 17, we're asked to determine the cell potential between copper and iron. Here we have copper ions forming solid copper and iron becoming iron ions. There are many cell potentials for copper ions, however, only this one shows copper 2 becoming solid copper with a cell potential of 0.34 volts and the transfer of 2 electrons. The same is said for iron. If we had a full standard reduction table where iron ions can become iron ions, but again we are looking for iron 2+ and solid iron, which on the table as a reduction potential is a negative 0.44 volts and the transfer of 2 electrons. However, this is not what is occurring in our reaction. In our reaction, iron is being oxidized. And so we're not going to use the reduction potential, but the oxidation potential. So we simply flip the sign. So when 2 electrons are transferred, our cell potential for this voltaic cell is 0.78 volts on the voltmeter. So far, we do have a functional battery as we have a positive cell potential. To calculate the Gibbs energy, though, we can calculate it by using our formula delta G equals negative NFE, where N is the electrons transferred, E is the cell potential we just calculated, and F is Faraday's constant, which is 96,500. So the Gibbs energy for this reaction is a negative 150,516 joules, negative 151 kilojoules. So yes, the reaction is favorable because delta G is negative and the cell potential is positive. These reactions are chemical reactions and will eventually establish an equilibrium. Therefore, they are subject to Le Chatelier's principle. If I increase the reactants or products, that will shift the reaction. Keep in mind that cell potential is calculated based off of 1 molar solutions. So if I were to change the molarity of the solutions, that's going to shift equilibrium in one direction or another. So for exercise 18, use Le Chatelier's principle to determine if the cell potential increases or decreases. In 18A, we increase the concentration of aluminum ions. The manganese ion stays the same because keep in mind, cell potential is calculated with 1 molar. So if I were to increase the concentration of a product at equilibrium, that product is going to collide more with the other product and shift the reaction to produce more reactants. Since I am favoring reactants, the cell potential is going to decrease because this reaction produces half a volt. So by making more reactants, that voltage decreases. In 18B, we increase the concentration of the manganese ion. More reactants means that more manganese will collide more frequently with aluminum, producing more products. Since the reaction favors the production of products and this voltage is a product, the cell potential will increase. Even though these are carried out in different half cells, Le Chatelier's principle still holds true. To calculate how much the cell potential increases or decreases, you use the Nernst equation. Now, the Nernst equation used to be on the AP exam. It is no longer on the AP exam, but it is on your quiz next class. So, the Nernst equation is temperature dependent, and as long as you're at 25 degrees, it's the cell potential minus a constant divided by the number of electrons transferred times the log of the reaction quotient. This means that as a battery runs, as this reaction quotient reaches equilibrium, you will gradually decrease cell potential to the point that when you've reached equilibrium, the cell potential is 0. A battery at equilibrium is considered dead. It no longer is thermodynamically favorable because at equilibrium, cell potential equals 0. So if you are at equilibrium, your reaction quotient is equal to your equilibrium constant, in which case this expression ends up equaling the cell potential. So a battery at equilibrium will eventually have a cell potential of 0. But along the way, we can calculate how much the cell potential drops. The voltage of your batteries does decrease over time. To calculate that, we'll use the Nernst equation. So for exercise 19, we have some cation that has a standard reduction potential of 1, and zinc cations have a standard reduction potential of negative 0.76. Whatever has a higher reduction potential is going to be reduced. So since this value is more positive, we are going to say that whatever VO2 cations are, they are going to be what is reduced, and therefore they are going to be our cathode. Zinc is going to therefore be oxidized. So we need its oxidation potential, which simply means we're going to flip the sign here. That means zinc is our anode. And if we look at the diagram here, sure enough, zinc is the anode and VO is our cathode. So that makes sense. In order to determine the cell potential, we'll simply add these values up to get a standard cell potential of 1.76 volts. This reaction is thermodynamically favorable because we have positive cell potential. In order to determine what the actual cell potential is at these conditions, since we don't have 1 molar, we will set up our Nernst equation, where the current cell potential would be the standard cell potential minus a constant over the number of electrons transferred times the log of the reaction quotient, which you remember from previous units is the ratio of products to reactants. Let's first talk about the electrons transferred. Here we have 1 electron needed for VO to be reduced. Zinc is going to give up 2 electrons. So we'll double this entire reaction. 2 electrons are absorbed from the 2 electrons given off. So N is 2. Our reaction quotient is the ratio of products to reactants. So the products here are going to be VO2 plus to the second, corresponding to the fact that we needed to double that reaction. Water is a pure substance, so it is not included. We flipped this reaction, so zinc cations are also a product. Reactant-wise, we have VO2 cations raised to the second times the concentration of hydrogen ions to the fourth, and then zinc metal is a solid, so it is not included for the same reason that water wasn't. And now it's just a matter of plugging in all of these values and determining a number. So we'll take our voltage and we will subtract from it 0.09296 times the log of 1 times 10 to the minus second squared times 1 times 10 to the minus first over 2 squared times a half to the fourth. So our reaction quotient comes out to be 4 times 10 to the minus fifth, 1.76 minus 0.0296 times 4 times 10 to the minus 6 gives us a cell potential, gives us a voltage of 1.89, because our reaction quotient must have driven up our cell potential. Our ratio of products to reactants was in such a way that we produced more voltage. Since the ratio of products to reactants, a concentration can change, it is possible to make batteries out of different concentrations, where the higher concentration is what's getting used up. until the concentrations of both reach equilibrium. So if we have a voltaic cell made out of 0.1 molar and 0.01 molar ferrous ions, we can determine which is the cathode and the anode. In one of the half cells, the iron is going to be reduced into solid iron. And in the other, solid iron will oxidize into ferrous ions. Since our half cells are based on concentration, the concentration of the higher half cell is going to come down, and the concentration of the less concentrated half cell is going to go up, meaning that the more concentrated cell must be our cathode, and the less concentrated cell must be our anode. And since electrons always flow from anode to cathode, the electrons are going to flow to the right. With that, you can do page 17 in your packet. Assume that all reactions are at 298 Kelvin or 25 degrees Celsius. Next class, you'll have a quiz where I'll ask you to label the parts of a voltaic cell. You'll have to find the cell potential, and using that cell potential from a list of 4, determine an unknown species. Meaning in one of the half cells, you will have an unknown metal. You have to tell me what that metal is. Basically line up the cell potential for that half cell. You'll have to write the overall chemical reaction given the new species that you determined, and then I'm going to change the concentrations, or I will change the reaction in some way. You have to tell me how cell potential will change using Nernst equation. Since the Nernst equation is no longer on the formula sheet for the AP exam, you will need me to share with you this equation on the board. Please remind me in class to do so. Next class, we will finish this by talking about electrolysis, which is when you have a negative cell potential or Gibbs energy is positive, a reaction that requires us to put energy in, or electroplating. I will see you then.